The dairy industry is integral to New Zealand's economy, generating nearly $20 billion in export revenue in 2020 alone. This wealth, however, comes at a cost. The industry releases 2.1 million tonnes of carbon emissions per year, which is largely due to the use of fossil fuel boilers for producing steam. Most of the steam is used for milk powder production during evaporation and spray drying. Reducing steam consumption not only reduces emissions, but it also reduces cost, and so it is common to see a combination of thermal vapor recompression used to recover evaporated water to be reused in the process in conjunction with mechanical vapor recompression, which has the same function but is instead powered by electricity. In our current dairy industry, it is uncommon to see mechanical vapor recompression exist in isolation. Our project focuses on completely electrifying the evaporation process, but in a design that also uses the minimum practical amount of renewable electricity in order to help decarbonize our dairy sector. A successful design has the potential to reduce emissions by more than 44% based on the current grid emissions factor. In order to do this, our design has to use less than 5.2 megawatts of electricity, which will also allow us to break even in terms of typical operating costs.
Our iterative design approach starts with acquiring stream process and composition data from literature and industry experts to create an Aspen HYSYS simulation. From the working model, we extract mainstream process data and apply pinch analysis to determine our heating and cooling targets. Pinch analysis also allows us to identify where to appropriately integrate our MVR units, heat exchangers, and heat pumps for improvements in energy efficiency and reduction in operational costs. We optimize our system by modifying process conditions such as temperature and pressure, or change the placement or amount of some of our process operations. We continuously update our parameters to eventually achieve energy targets that satisfy our project objectives. Our final solution encompasses our model and each of our individual sub-projects. Along with conducting impact analysis, we continuously communicated and shared our results with Fonterra, Tetra and Pillar to ensure that our solution is feasible and practicable.
We considered various aspects to ensure that our solution is working within the current standards. For product safety, the process had no direct heat exchange between synthetic refrigerants and processed milk. Instead, the team used some of the water that was evaporated from the milk, called cow water, as an intermediate fluid. To keep within the process safety standards, the milk was heated to 60 degrees in one heat exchange, which would prevent rampant thermophilic bacterial growth. Alongside minimizing operational cost, operability and control was also important, which led to experimenting with different technologies such as direct contact heating versus traditional heat exchangers, and integration of innovative products such as the vapor fan, while ensuring all other considerations were met in the design of the process. The culmination of these considerations was incorporated in our final design of an electric milk evaporator system, which features an optimized preheating process design which uses minimal electricity and will be easy to clean and operate. The key features of this process design includes the use of 2 direct contact heaters for fast heat transfer and process simplicity, as well as a 3-stage vapor fan that upgrades excess vapor in order to substitute steam that would have been traditionally supplied from a fossil fuel boiler. Electricity-powered technology, specifically transcritical CO2 heat pumps, and 2 MVRs provide the additional heat the process requires to drive the evaporation and heat treatment. The concentrated milk from the evaporators and the CIP water would be heated using separate air-sourced ammonia or CO2 heat pumps, allowing for tighter control. Through the use of process simulation, our entire design was rated to use 3,541 kilowatts, which was well below the economic break-even point to displace fossil fuels, and therefore indicating a successful design.